In last lecture, I am discussing application of crystal field theory to tetrahedral complexes. In that, we have discussed about the tetrahedral complexes have four ligands. They are placed at the regular four corners of tetrahedron. Then these four ligands are placed in between the axes x, y and z. They are not directly placed on the axis, therefore repulsion energy on the axis decreases and repulsion energy of x, that is repulsion energy of T2G, increases. If you will concentrate on this diagram, splitting diagram, T2G at the higher level and EG at the lower level, which we have discussed already in last lecture. Now I will proceed towards the next part, that is the tetrahedral field is weaker than the octahedral complexes. That is the magnitude of the crystal field splitting, that is delta T. Delta means small change and T is tetrahedral. The distance between the T2G and EG, distance between the EG and T2G, distance between the EG and T2G in tetrahedral field is termed as delta T. Okay, the distance between the EG and T2G in tetrahedral field is termed as delta T. This delta T is less than delta O. Delta T is approximately 4 by 9 times. That is, delta O is stronger than delta T. So, many times we ask this thing in competitive exams or MCQs, that is what is the relation between delta T and delta O. You must know that delta T is equal to 4 by 9 times delta O. That is, tetrahedral complexes are always high spin, that is they have only weak field ligands, they are weaker. You have to treat them like a weak ligand complexes. No tetrahedral complexes with low spin configuration have been formed, means no strong complexes are formed. This is due to the quite small crystal field stabilization energy in tetrahedral field, and it is always less than pairing, means the electron can singly arrange first and then they will jump to the higher level. They will not pair up at the lower level, they will jump at the higher level. Pairing energy is more than the delta T. Pairing energy is more than delta T. So it is the CFSE, that is crystal field stabilization energy in tetra field, it is quite small. It is always less than the pairing energy. So pairing energy does not occur and the complexes are high spin complexes. Pairing energy does not occur, therefore complexes are only high spin complex. Now the examples are TiCl4, that is titanium chloride or tetrachlorotitanium, magnesium oxide, chromium, cobalt chloride. These are the tetrahedral complexes. Ligands, why there is a possibility why tetrahedral complexes may form, why there is a possibility, because ligands sometimes are bulky, they cause crowding in the octahedral system. At that time there is a possibility that tetrahedral complexes are favored. Sometimes ligands are weak. In the case of low oxidation state of metal ion, there is a possibility of formation of tetrahedral complexes. This is the continued part of the last lecture. Actually, what you have to remember, that there are four, you have to make a cube, then you have to make you have to place the ligands, and that ligands must be at the corners of tetrahedral, that is tetrahedron. The ligands must be placed which are in between the axis and not on the axis. When they place in between the axis, the energy of the that lobes increases and the energy, that is EG orbital, decreases. Therefore in case of tetrahedral complexes, you can see the behavior exactly opposite to the octahedral complex. That is, in case of octahedral, T2G at the lower level and EG at the higher level, whereas in case of tetrahedral, the T2G at the higher level and EG at the lower level. This is all about the application of crystal field theory to tetrahedral complexes. Before moving to the applications, you must remember that in this case only we have this one type of treatment, that is one type of system, that is only high spin complexes, only high spin complexes, that is weak ligands. So in the octahedral system we have made two types, that is one is strong field and another is weak field. But in case of tetrahedral system you can see only one system, that is weak ligand system, or also called high spin. In this case what you have to remember, that EG at the lower level, so two orbits at the lower level, and T2G at the higher level, that is three orbitals at the higher level. Now in case of crystal field stabilization energy of tetrahedral complex, that this difference is given by delta T, that is small change or a small difference between the EG and T2G. It is denoted by the delta T, that is small change in tetrahedral system. EG will be lower by minus 6 dq and T2G will be higher from the barycenter, that is up to the plus 4 dq. Now this is all about the today's part. From next we will calculate the crystal field stabilization energy of the tetrahedral complex. Thank you.